Good morning. Welcome to MSC Group's FasTech seminar series hosted by WestTech Sales and TMC. Thank you for joining us. Today we're presenting Powering the Future of Vision, Qorvo's PMIC for Connected Cameras. Our speaker for this seminar is Upal Singupta. Upal is a field applications engineer for Qorvo Power Products, supporting customers in the Midwest, Northern US, and Canada. He has over 30 years of industry experience, including OEM product development and the consumer electronics, telecom, and automotive industries. Most of Upal's work has been related to portable power, battery management solutions, and charging systems. Throughout our presentation today, we'll keep everyone muted, and then at the end, we'll open it up for a Q&A. And with that, Upal, I'm going to turn it over to you.
Okay, great. Thank you, Amanda. Can everybody hear me all right?
We can.
Okay, great. I'll go ahead and share my screen. And yes, as Amanda said, we're going to talk about Qorvo Power Management today, and the idea, and specifically with the application towards what we call connected camera applications. This could be a number of things, right? But what you see, it's not necessarily just an individual camera like this, but many systems such as robotics, drones, other types of industrial equipment are obviously incorporating intelligence and vision into their functionality. And so the difference, why we call them connected cameras, is typically all of these systems, whatever the application, are not just a camera, but they have a number of other interfaces, particularly wireless interfaces, either through Bluetooth, ultra-wideband, Wi-Fi, all kinds of different connectivity associated with transferring that image or using it for another reason. So what you end up with is a system that requires multiple power rails. Like even if you look inside a mobile phone, many people don't realize that inside a mobile phone you might have 15, 20 or more separate power rails to operate the different subsystems inside that product. So the connected camera is going to be similar. And typically you would need many, many different power supply circuits to operate all of the functions, the memory, the processor, the camera processing itself, and the connectivity and communication functions. So one of the things that becomes a problem is that if you have space constraints, trying to implement this on a small circuit board becomes very challenging. So what we'll talk about is how you can address that problem using the Qorvo PMIC Power Management Integrated Circuit, in case you don't know what that stands for. But that is typically a single chip solution that will have multiple power outputs from one or two or sometimes even three different inputs, the input being the battery, potentially a wireless power source, or potentially an external DC, whether it's a USB Type-C connection or some dedicated DC plug-in input, right? So we'll get into what that involves in terms of a block diagram here, the next slide. So Qorvo has multiple technologies that we develop in our IC portfolio. We are primarily known as a wireless communications company, right, with RFPAs, low noise amplifiers, as well as connectivity solutions, Bluetooth low energy, or ultra wideband, things like that. But I am part of the power management division, as is my colleague Ben, who's here with us today. So we're going to talk about the power management aspect of that. Right? So we develop multiple things that could go into a connected camera. Today we're going to talk about the power aspect of that and how you could power some of these other functions in that system. Okay, so here's an example. I mean, the basic idea, I think most people recognize that what a PMIC is essentially multiple voltage regulators, switch mode, buck or boost converters, linear regulators, maybe some load switches, which are just basically turning subsystems on and off selectively. And it's something that typically has some type of digital interface to your system processor. This is showing an I2C interface. Some of them use SPI interfaces. Some may use other custom, digital IOs to control them, GPIOs, right? But if you look at, what's involved, right? If you go back to the block diagram, all of the things that you have in the system, this is more of a physical representation of that. Obviously, you have a battery, you have some memory, you have the camera module itself, you have Bluetooth interface, You have other types of memory. And then here in the corner, you have a single PMIC that powers all of those things from your input, whether that be the battery or the external charger, right? So this is an example of one of our parts. I'm not going to beat this to death in terms of the details, but essentially we have multiple functions. This particular IC has 13 different voltage rails. It will take an input that represents potentially the lowest voltage the battery could be up to the highest voltage that a typical USB charger could be. Right? We have some others with wider ranges. Most of them are targeted around the single cell lithium ion battery and or the external USB charger as a power source. But the goal here is to get things smaller, right? That if you tried to do this, if you tried to make 13 voltage rails with standard off-the-shelf parts, right? Even an LDO, if it's a 1x1 or 2x2 part, switch mode regulator could be a 2x2 millimeter part. Once you add up all of those, you're going to take up a lot of board space just for the power. And the goal here is to integrate that into the smallest possible space so that you can make a compact product design, right? And at the same time, if something is battery operated, you want it to be very low operating current when these regulators are not being used so that you have good standby life when you're in idle mode. The other thing that sometimes we forget about is when you have multiple discrete power solutions, they all have their own input bypass cap, all their own output capacitors. When you have an integrated solution, you can double up, right? Particularly if you're feeding one of these converters from the output of another one, you can share input and output caps. You can have a common large input bypass so that you don't need as many discrete components when you use the integrated solution, in addition to not needing so many discrete voltage regulator chips. And here's another example. Again, I'll spend a little less time on it. It's the same idea, but the point is that this is our, I guess I would say, our most complex device with the most number of outputs. It has 19 different voltage rails in a single chip. It's the 88911. So our products range, in a variety of complexity. I'm just going to skip forward to this page here. I'll come back, right, just to give you an idea that we have devices that have a smaller level of integration for a simple end product, right? 2 or 3 switch mode converters, couple of linear regulators in relatively small packages. Our highest integration parts, as I mentioned, this one has 19 different rails and supports a wide variety of inputs. So this kind of gives you the spectrum of if you have a relatively simple function where you need a couple of rails and something simple, relatively lower cost, up to a complex array of features and a lot of programmability. This is the range of products we have. We have about 20, 25 different parts we're adding to that portfolio all the time. So I'll get into now what, when we use the word flexibility a lot, right? Because yes, this is I don't want to call it a custom part, but it's a somewhat unique part depending on what you use. It's not just taking a bunch of 3-terminal LDOs and a bunch of little single chip switchers and hooking up how you want, right? You have everything in one package. So if you want to be able to use it for more than one specific design, you need programmability, right? And that's why these all have I2C or possibly SPI, as well as GPIO inputs to control what they actually do when they power up, right? Additionally, in these diagrams, for simplicity, we showed the VIN coming in, powering all of the rails, and then an output, right? If you look at the details, each of the regulators actually have their own VIN pin, right? So this is VIN for the buck regulator number 1, VIN for the buck regulator number 2, and so forth. Typically, if you have your battery or your USB source, that VIN is then going to be tied to all of these. But if you have a situation where you want certain stages to be powered from different inputs, you do now have the flexibility to tie the input of any converter or regulator to wherever you want it to be powered from. So for example, if you had set this up where you had some of these buck converters at 2.8 volt output, 3.3 volt output, whatever they are, you have a linear regulator that you don't want a lot of heat. If you have for example, a 1.5 volt output linear regulator, you could run that from a 2.2 volt buck converter output so you don't have all that loss across the pass element, right? So you do have the hardware flexibility of setting up your power tree or topology however you want. But additionally, you have some programmability, which we get into here, right? So Again, when you have multiple regulators, at any time during operation, you can write an I2C command to change the outputs of these voltages. However, the first question is, well, when I first power up, what are they going to be? Right? So each of these buck controllers has a range of outputs, for example, minimum 1.0 and maximum 3.3 or something like that, right? This is a variety of different things. Could be 2.8, could be 1.2, could be all kinds of numbers. Each of these devices internally, I'll go back here, when you say the digital stage has some memory, right? So that memory, it's non-volatile memory, but it is electrically erasable. So when we build the part, set up a memory map internal for some default values. So that regulator powers up with specific default values for each of the regulator stages and default values for the sequencing. That is, out of all of these rails, which one comes up first, which one comes up next, do these two come up together, and so forth. So that's built into the default memory map. We can provide you with a tool. There's a couple of different tools that we have that allow you to program that part, to experiment with different versions. Once you decide on your memory map that you want for your default power-up value, you would provide that to us, and then we would build the part with that default setting so that on initial power-up, you get a configuration that can get your system up and running. Once your system is up and running, of course, then your processor can modify things. So sometimes, if you want to go into a low power mode, or if you want to go into a high power transmission, if you have an RF interface, you can change voltages, right? Sometimes to operate certain subsystems, you may modulate that voltage up and down depending on what it's doing, right? So, skip forward to this. Typically, the PMIC power is up. Your system can read whatever those settings are. You can modify them, change things in real time. If you shut the system off and do a power cycle, it'll come back up to those default settings. And this consists of all of these individual things. It's not just what the voltages are in the sequencing. We have programmable delays between rails coming up, GPIO interfaces, soft start, current limits, all kinds of stuff like this. So everything, or at least many things, are going to be configurable and adjustable. So you can optimize your system. Obviously, in any battery-powered system, you want to save quiescent current whenever you can. So if you aren't doing a transmission, if you're in a low-power mode, you want to shut certain things down, lower sampling rates on A to D converters, whatever, right? So you can change all kinds of stuff. And again, here's an example of that flexibility that we like to talk about, right? That for a given part with some number of switch mode converters, some number of LDOs, it can be set up as a default startup to operate different devices, as long as it's the same number of power rails. But say you need a different sequencing. Say one of the switchers needs to come up first, or one of the LDOs needs to be always on to operate some kind of backup system. And when I talked about that memory map, that's this dash number, right? So whoever needs a particular configuration can decide that, again, with the development tools that we provide with our eval kit. You set it up the way that you need it to be. You let us know what that is, and then we would manufacture a version with a dash number corresponding to that particular memory map. Once you're powered up and running, we'll give you this tool so that you can see the sequencing. You can see, the effects of all that through your development process. You would set it up the way you need, and then we would issue. We would make the part according to a certain dash number. Now there is, of course, a minimum volume associated with this due to the cost of us developing that version. One of the things that's good to know for some lower volume applications is that we already have a library of a number of these. So if there's a particular memory map configuration that exists that could at least get your product started up and running initially, then your microcontroller can then modify that. That would be even invisible to the user. It powers up, and before the display even comes on, you could change what you needed, and then change levels on the fly so that you can operate your product however you want it. Right. So again, I'll leave that at this example showing the the range of products that we have, from the relatively simple 2, 3, 4 regulators up to 10, 15, 19 different rails in one part. Right. And of course, the higher density parts are going to be in chip scale packages versus QFNs, just because of the density that you need. But we can supply a number of different configurations that match many different application requirements, right? So getting into a more concrete example of how you use this, in a real application, right? As I mentioned, the main products that Qorvo is known for historically and today, right? The vast majority of Qorvo's products are RF communications, wireless communications type systems. So this QM3582X is a new series of ultra-wideband SoCs that we are launching. We have some ultra-wideband products on the market. We'll be growing that product line. And of course, since our team does power management, we thought it would make sense for us to do power management that's targeted at these Qorvo communication systems. So if you look at what the ultra-wideband chip requires, it has about a half a dozen different power rails. This shows 4 or 5. Some of them can be tied together, right? They operate the different functions, right? Some are communications with the external processor. Some are the RF stages that go out to do the transmissions or the receptions, the receiver or the transmitter. This part supports multiple data rates. I'm not a UWB expert, so I won't dwell on this, but the idea is that this is an integrated solution to provide all the functionality you need in an ultra wideband application. So how do you implement the power for that? Well, first, figure out what the requirements are. What are all these VDDs? Well, what's the values of those? How do they have to come up? The conventional approach, right? We built a board to show if you used discrete voltage regulators, 2.8 volts, 1.2 volts, whatever these need to be, what would that look like? And this is a distributed solution. Again, Qorvo does power management, but for the most part, we do these somewhat more specialized type of systems that are highly integrated. We are not doing the garden variety, 3-terminal LDO, with a 5-volt in, 3-volt out, DC to DC, because that's basically a commodity product. There's already a lot of products out there in the industry that do that. And right now we're not getting into that game because it's kind of a race to the bottom. It doesn't really provide anything special. You already can get those from a dozen or more suppliers, right? What we are doing is taking all that functionality, putting it into a single chip. And this is an actual board that our reference design and apps team has built, right? So you can see physically how much space you're saving, right? It's about, I think, roughly, 75% reduction in the total PCB space that you need to do the same function, right? And again, that's this particular chip. This is just a quick bullet list of what does it do. It's 1, 2, 3, 4, 5 voltage rails, programmable interface, and some GPIOs, right? Versus 5 separate regulators. Okay, so again, this was just a very quick introduction. These are the questions that we would talk to you about if you're interested, right? We can probably come up with a good solution for what you're doing for these types of applications, but we always start with what is your power tree, right? What is your the number of rails you need? Do they need to be switch mode? Do they need to be linear? Do you have preferences? Once we know that, we can set up the interconnection of what's your input source, how many different outputs you need, how do you string those together, what do they need to power up to in default conditions, what order they need to come up in. And then from there, we can look at the other things, particularly, with the LDOs, do you need particular specs such as PSRR or quiescent current, things like that. What kind of packages do you need to look at? We have some flexibility there, but in general, what are you looking for in power? As I mentioned, we have a range of products. I'm going to go off script for just a minute here and bring up the Qorvo website to show you. Okay, if you guys see the website. So if you look at the Qorvo website and you go to Power Solutions and you go to PMICs, what you'll see is we have about 20 plus different PMICs, right? And this gives you a quick description of what the functionality is. These columns will tell you how many switching, how many buck regulators do you have, how many boost converters do you have, if any, how many LDOs do you have? You have to kind of roll across and see the rest. But this is kind of an easy way to figure out, okay, I need X number of rails and I need this combination. In some cases, if you're using a particular processor, this will give you some ideas of what is it already tested for. But even if you're not using these, you can figure out probably from the combination of outputs, do they roughly meet the system requirements that you have, right? But as you see, we have about 20 different parts and with different combinations of functionality. So there's a good chance that we can, at least give you some basic thing that would allow you to start up your system, and then you can, modify the outputs with the I2C commands. There's also a separate document here that will, give you some details of what I've been talking about. Okay, so let me get out of here, and I'll leave it at that. And that's essentially the story as far as the introduction.
Thank you, Upal. If anyone has any questions, please feel free to unmute yourselves and ask, or I can monitor the chat, and we can answer any questions you may have. And then I am going to launch a quick poll. And this is just for some quick feedback for us. Does anyone have any questions?
I have one question. Is there any protection against writing an incorrect voltage on the fly when your PMIC's up and running? So like, for example, password protection or anything like that, or you just have to make sure you don't make a mistake in software?
Well, I guess that is, I'm not sure I can give you a complete answer to that. What I do know is there are certain registers that are blocked, right? We have parts of the memory map that are not user writable, for example, right? And some of those do involve the safety things, the calibration of regulators and so forth. What I would say is that, if you look at a data sheet for a part, each of the regulators will have certain ranges that they can support, min and max, right? And they're not all the same, right? Some regulators are set to be, for example, 1.0 to 2.8. Others are set to be 2.0 to 3.3, for example, right? So what I would suggest is, we would look at the device that the min and max ranges of each rail is connected to something that can tolerate that, if that makes sense, Sam.
Yep, understood. That makes sense.
Okay, so I mean, again, it comes down to your specific requirements and what you're trying to do. And as I noted, the first question we always ask is, what is your power tree? What are you connecting stuff to? And if you can figure that out, then we can work with you to come up with the right part that would hopefully give you a robust or reliable option.
That makes sense. Yep.
I haven't seen any others come into the chat. So with that, we can wrap up. Upal, thank you so much for the great presentation. Right. And thank you everyone for joining us this morning. Right. We have recorded the seminar, and we're going to send out the link to the recording as well as the slide deck. And please feel free to share with any colleagues. And if you have any follow-up questions, please touch base with WestTech or TMC, and we can get you in touch with Upal if needed to answer any more technical questions.
Sure. Or Ben, I would just add that, Ben and I are both here. We have the same job in different parts of the country, right? Ben is based on the East Coast. I'm based on the Midwest. So Ben, you want to say hi real quick and just let folks know which regions you support?
Sure. Hi, everybody. I am based in South Carolina, and I'm Upal's colleague doing the same sorts of things and covering essentially the Eastern time zone. So Ohio, for instance, is mine all the way down through about Mississippi. So anything kind of there in the East is going to be mine, but you can go to either one of us and we'll certainly get inquiries to the right places.
Yes, we do talk to each other on a regular basis, so it's all good. You can contact either one of us. But thanks, Amanda and Robin and all the folks for organizing the session. And thanks, everybody, for joining.